So here we have Christiana and Madison Utterback from the Intercollegiate Biomathematics Alliance, and they will be presenting on a computational modeling approach to understand the outcome of ischemic hepatitis. And now you guys are welcome to present.
Awesome. Thank you so much, guys. So like Anna said, we are presenting on the computational modeling approach to understanding the outcome of ischemic hepatitis. I'm Christiana Beard.
And I'm Madison Undergraduate. Thank you again for joining us. So we'll go ahead and get into it. Oh, we have to go to our slide. Okay, perfect. Yeah. So just a little bit of background info on our project. So ischemic hepatitis, which we'll refer to as IH throughout because it's kind of a mouthful. It's a severe liver injury due to the necrosis of hepatocytes, which is just the death of liver cells. And there are numerous underlying conditions of IH, such as shock, so like allergic shock or cardiac shock or septic, or it can also be from an ongoing trauma, so such as like heart failure, like chronic conditions. But no matter the underlying condition of IH, they all lead to similar results in our body, which is just a decrease in oxygen. So whenever oxygen is not being delivered to organs, namely in our case, the liver, the organ starts shutting down, and so that will lead to liver cell death. And whenever the liver goes into failure, we're able to pick up on some serums that increase, and that's what we kind of measure to indicate, hey, someone is going to liver failure and there's a problem. So motivation behind our project is that IH is currently undiagnosable, except by the process of elimination of all other liver injuries. So if someone comes in with liver failure and a doctor will go through all the tests of all other liver injuries, and it turns out it's none of those, they'll just go to default that this person must have IH. And so kind of the problem with this is that IH is preventable, but only when it's diagnosed within a timely manner. And again, since it is the last resort, this isn't typically the case. And so it does have a 50% fatality rate when those underlying conditions are untreated within that time frame. And so we're here to try to find a model that can help determine the outcome of an IH patient.
Okay, so now that we kind of have the motivation for our project, we now look into gathering some data. So the place that we got the data was actually through ALFSG. And basically what it did was, this is a group that went across multiple centers in the US, just anonymously collected, and it was from real patient data. So some of the variables that they collected were AST, ALT, bilirubin, creatinine, and INR. And these are kind of just the main peak values, and with INR being a test. So the reason why we kind of looked at these is because whenever a patient goes in to look at their liver, these are some of the main things that any kind of doctor looks at first. And for independent variable, we chose outcome, and this is coded as 0 for survival or 1 for transplant or death. Okay, so now that we've kind of described what our data is, we will now look into just some visuals and then some descriptive statistics. So on the left side here, we have a little table of our data, and it shows the mean, median, null values, and outliers for each of them. And on the right side here, we have the histograms of a couple of the just kind of demographic data here. And the first one shows the age of the patients. So from this visual, we can conclude that most of our patients are between 50 and 60 years of age. Our lower graphic here shows the admission days. So, and then we can also see from this visual that most of our patients had an admission day less than about 5 days. Okay, so now that we've described our data, we want to look into some of the objectives. So the first one is we want to identify the most significant biomarker in predicting the outcome of a patient with ischemic hepatitis. Then our second objective is to apply computational models to predict an ischemic hepatitis patient's outcome based on the attributes of the BART markers. So here we have our methodology mapped out. And first we went, just to clarify too, we were able to do all of this in R. And the first step that we did was data cleaning, and then put that into training. Some of our models that we have here start with logistic regression. We also had regression trees, and then BART for a boosting method. And we also had the SMOTE method, which gives us a different kind of different kind of training set. So once we had that new training set, we are able to put those back into 3 of our models and then evaluate them using some of our testing methods. And that included the accuracy, ROC, and AUC, sensitivity, and specificity. Okay, so the first method that we tested was logistic regression. So basically, the model provides the probability of a success happening based on the linear combination of the independent variables and their parameters. The reason why we looked into this method is because it is one of the most simplest binary classification models. And then once we had the gen model, we looked into a way to kind of test if some of our variables were significant. And we looked to using the stepwise model selection. And then again, it just answers the question as to if all of our variables are significant. Okay, so this kind of shows the results of what we got from logistic regression. And whenever we put in all of our variables, this is kind of the general function that we got, as you can see there. And then below we see the result of using the stepwise model selection. And we found that both bilirubin and INR were found to be significant. The second method that we used was regression tree method. Basically, this is a decision tree used to predict a quantitative space. Visually, it looks like a tree that shows the logical flow of a decision, and its outcome are seen as terminal nodes. So the reason why we looked into regression trees is that it outputs a nice visual that is easy to interpret. Some of the steps that we used in this algorithm were first, recursive binary splitting. This is to build the tree. Second step was pruning, and that was to kind of cut back some of those nodes to make it a little bit more easier to interpret. And the third step was k-fold cross-validation. Okay, so here we have some of the results of our method. The first thing we did was specify the deviance criterion for recursive binary splitting. The second step, we made sure to prune back some of our nodes, and we went from 12 to 7 nodes and specified a cross-validation set of 5. So in our visual here, we see just kind of the tree-like structure, and the topmost node here shows INR peak. This is the first split, so we can conclude that this was the most significant variable in our tree. And if we look at the terminal nodes here, we see that some of these numbers may not be perfectly 0 or 1s. So this is where we either round them to a 0, which is survival, or 1, which is death or transplant.
Okay, so onto our third method that we applied to our data set. We use the Bayesian additive regression tree method, also known as BART. And this is a relatively new method that was first proposed in 2008, and it's based on Bayes' theorem. So in case you forgot what that is or just aren't sure, this just predicts a ladder distribution from a prior distribution or former one. So this is really helpful with the regression tree method because it keeps individual tree effects small. So whenever we build like a small tree, we'll learn from that to make the next tree, and then we'll learn from that one to make another one. And so this is how we kind of get the sum of trees model that it's based off of. And then another benefit of using BART is that it's able to identify variables that are more important when explaining the variation of an outcome. So keeping that in mind, I've included the variable importance output that we got, and these numbers represent a count. It's the number of times a variable was used as a decision factor for like a split in a regression tree, and then divided by the total number of trees. So that's how we get some decimals. So here we can see that bilirubin and INR were our most important factors, which actually is kind of similar to what we got with both our logistic regression model and with our regression tree. So another method that we applied to our data set was the synthetic minority oversampling technique, or SMOTE. And so what this was proposed in 2002, so it's also newer, but probably more well-known than BART. And so what this helps with is unbalanced data sets, and it helps balance them. And so in our case, it undersamples our majority class and oversampled the minority class, whereas some techniques usually just undersample, or some will just oversample, depending the class that needs to be like balanced. But with SMOTE, it makes synthetic data points rather than oversampling with replacement. And so in our case, this was really helpful because we had a pretty unbalanced data set. So we used SMOTE and to balance our data, and then we applied the 3 methods that we just went over using this new data set that was balanced. So here's a visual of our data before we applied SMOTE. We had about 154 observations. As you can kind of tell from our blue and red dots, it was about a 25 to 75% split, with the blue dots being our 0 or survival, and the red dots being our 1 or death and transplant. Another thing to note are the axes on our graph. So we have 2 of our biomarkers, AST and ALT, plotted. We could have chosen any biomarkers really, but here we were able to see that AST and ALT are correlated. And so we'll kind of address that at the end of our presentation, but I did want to bring it up now. And then after applying SMOTE, we can kind of see that there was an increase of our minority class or our survival. And so after we applied SMOTE, we had about 230 observations with a pretty even split of 50-50. So using this new data set, we applied the models, like I mentioned.
Okay, so going back through them again, first logistic regression, we did the same steps, and this is kind of what we got for the first method, as you can see there. And then under stepwise model selection, we actually found a little bit of a difference between having SMOTE and not having SMOTE. We see that we now have INR, AST, and creatine. The second method was again regression tree, and we went through the same steps. And when we got to the pruning step, we went from 17 nodes down to 5 nodes. And again, as you can see from the tree here, our topmost node has bilirubin instead of INR. So bilirubin seems to be the most significant one in this model.
So then we also applied BART with our SMOTE data set, and the variable importance also changed a little bit. So we have AST and INR. So INR was still relatively important, but we did see AST here. And now to kind of compare all of these methods that we've thrown at you in just a more condensed way. So at the top table here, we have our methods of our original, using our original data set. And as you can see, I do have the accuracy column kind of highlighted because accuracy is not a very good predictive measure of a method with an unbalanced data set, which we had originally. For instance, if we predicted all death or transplants for all of our outcomes, we would automatically get about a 75% accuracy because we had 75% in our data set, roughly. And so then we also provided the AUC value, which correlates to our ROC curves that we'll see on the next slide. And then we have sensitivity and specificity. So sensitivity in our case is telling us how well our model predicts a survival outcome, or correctly predicts a survival outcome when the outcome is actually survival. And then specificity predicts is when our model predicts a death or transplant outcome correctly. So in general, sensitivity and specificity are inversely related, which we can see here in just our general methods. We see sensitivity is typically lower, whereas our specificity is higher. So again, just from that inverse relationship. And then in our second table, we have our methods with our SMOTE data set. So the accuracies don't look terrific, but I think it was pretty promising. We have our AUC values again, and then I also want to address the sensitivity and specificity here. So with our balanced data set, our models were provided more of our survival outcomes, so they were able to better predict them. So our sensitivity increased. And then with that inverse relationship, that an increase in sensitivity is going to naturally decrease in specificity. So we kind of see an opposite relationship between these two with our methods with and without SMOTE. So on this slide, we do have our ROC curves of all of our methods. Like I said, the AUC value kind of correlates to this. And these are just plotting the specificity versus the sensitivity. And it's basically just a graphical interpretation of our results, because sometimes a whole table of numbers can be overwhelming. But the general pattern that we see here is that our methods performed better with our SMOTE data set when it was more balanced than unbalanced. And so our conclusion overall at the moment is that our SMOTE data set provides better models, and specifically BART had the best AUC values. So we would say that's the best model for our current prediction.
And now that our slide is mostly done, we wanted to address that, well, our research is not done yet. We still have a lot more to do. So a couple of the things that we wanted to look into from here was first, applying neural networks. We are still in the process of trying to learn and implement this method. And then for the second one, we also wanted to look into the multicollinearity issues. As we have seen previously, AST and ALT were very highly correlated. So we did want to address that later. And then the third thing we wanted to look into was collect a bigger data set. And hopefully something that would include information on the oxygen delivery to make a more robust prediction model. So here are some of the main references that we've used just at a glance. And that's pretty much it. Thank you so much for being here. Just open that up so you can zoom. Yeah.
Thank you. It's a really great talk.
Thank you.
I guess my question, I'm less familiar with statistics methods, so I don't know some of the methods very well. So I guess my first question is, did you learn those methods to do this work, or those are the methods that you have learned before? So after understanding the biological medical topic, you decide I'm gonna use this set of method to study it. So I guess my question is, which one comes first?
So we actually didn't know many of the methods. And here we first had to look at regression trees. That's kind of what we started out with. Did lots of coding with that. And then once we learned about some of the background data and then applied that method, we found that there was still some things we wanted to improve on. So that's kind of where some of the rest of the methods came into play. But again, we did have to learn those methods first before actually applying them.
So you learned those methods for this project, not like you learned this method in your coursework already, and then you get this project, you decide, hey, that's the method I've already know before, so I'm gonna use it. So you kind of like, you were told we're gonna use this method, you learned it, and then you get more details with the project, right?
Yes.
Yeah, just try to think about the idea. I mean, which one comes first, which one comes later. And you also talked about you want to more data, such as including like oxygen level and things like that. So what gives you the idea of oxygen among all the other things. I mean, I do biomass modeling a lot, so picking up important factors, sometimes it's not super intuitive because I don't really know that much. So what gives you the idea I'm gonna look more data, in particular providing oxygen level? Like what's the
For sure, data is always something that you want more of. Like when you're trying to make the model a bit better, data is always better. And for oxygen,
I would say in this case,
yeah,
I know our mentor she like has worked with this kind of previously in a different way. The oxygen levels would help with those underlying conditions, like diagnosing that, which can, again, diagnosing the underlying conditions and being able to treat that can help treat IH or help diagnose IH. So that's just like another biomarker or factor into this disease that would be beneficial in our data set. Seeing, hey, is this actually a better contributor to like diagnosing it than these other like serums that we have like measured.
So when you get access to the data, do you run into issues of like a lot of, let's see, missing entries? For example, this one doesn't have.
Yes, because it is real patient data. We had it in our little table. We had quite a few missing values. I think probably
about like 20% data loss just from null values.
So,
which sounds horrible, but I mean it's real patient data, so it also makes sense. It's hard to get that data.
Yeah, that's nice. Yeah, it's really interesting work. So you plan to continue working on it?
Yeah, absolutely. It's ongoing.
So you work during the semester, or it's continuous in the coming summer? What's your like?
We've been working throughout the semester. So it's been a bit slower than we were able to do during the summer because we have like our course loads now, but we're pushing through. It's really exciting to continue working on this because we learn stuff all the time. Like we'll catch our mistakes because we are learning, and then so it's been a lot of fun.
Originally, it did start out just as a summer project, but then we kept saying like
we can do better.
Oh,
like
we can do better.
Keep going.
Oh, there's that thing we want to learn
more.
too. Oh, we could apply this. So I think it's just the love of research. It just doesn't stop. You just want to keep improving.
So you two are junior students?
Yeah, we're both
seniors.
Yeah.
Senior. So you've applied for grad school?
I have, but Christiana has not yet.
I'm not currently looking into going immediately into grad school, but grad school has definitely always been on my mind. Yeah, definitely want to look into it soon, but yeah, for now.
Good. It's great work. Thank you.
Yeah, thank you so much.
I appreciate it.
And keep up the good work. Thank you.
Thank you.
Awesome. Thank you.
Yeah.